All right, let's get right into it. When you hear the term negative energy, your mind probably jumps to bad vibes, right? A toxic workplace, maybe. But what if I told you it's a real physical concept? Something so wild it could literally be the key to building wormholes and warp drives. Yeah, today we're peeling back the curtain on the actual physics behind one of sci-fi's greatest hits. And this, right here, is the question at the heart of it all. Because the secret to bending space-time, to traveling between the stars, it might not be hiding in giant suns or massive galaxies. It might be waiting for us in the absolute total emptiness of space. Turns out, the key might just be hidden in what we all think of as nothing. So what exactly are we talking about here? Well, in physics, the vacuum of space isn't really empty. It's fizzing. It's alive with this baseline energy called zero-point energy. Think of it as the universe's idle state. Negative energy is what happens when, just for a blink and you miss it moment, the energy in one tiny spot dips below that baseline. And this isn't just a cool idea, it's a real thing predicted by quantum mechanics. Now, I know what you're thinking. This all sounds a bit like chalkboard theory, right? Stuff that only exists in equations. But it's not. We have actual, measurable proof that this is a real feature of our universe. And that proof comes from an experiment that seems to pull a force right out of thin air. Okay, so picture this. It's a famous experiment called the Casimir effect. You take two perfectly smooth, uncharged metal plates. You put them super close together, inside a perfect vacuum. Now, according to all the classical physics you learned in school, what should happen? Absolutely nothing. They're just two bits of metal hanging out in empty space. But something does happen. An unexplainable force starts pulling the plates toward each other. It's not gravity, it's not electromagnetism, it's a force that comes from the vacuum itself. So here's the deal. Outside the plates, space is fizzing with all sorts of quantum energy waves. But the tiny gap between the plates is so small, it can only fit very specific, smaller waves. This creates more energy pressure on the outside, pushing in, than on the inside, pushing out. That space between the plates is now in a state of less than zero-point energy, a negative energy state. And boom, the plates are pushed together. And get this, it's not just some vague idea we can't pin down. We can calculate this force with incredible accuracy. This is the actual equation for that Casimir force. Scientists have gone into labs, run the experiment, measured the force, and their results match this formula perfectly. This is it. This is our undeniable proof. The force from nothing is real, which means the negative energy state causing it is also very real. Okay, so that's the crucial takeaway. Negative energy is real, and it has effects we can actually measure. So now, let's get to the fun part. Let's explore what this completely bizarre property of the universe could, in theory, let us do. This is where we step right into the world of science fiction, but with our feet still planted in real physics. Check this out. On the screen, you see the two most famous ideas: wormholes and warp drives. Now, they're totally different concepts cooked up by two different physicists, Kip Thorne and Miguel Alcubierre. But look closer. You see it? They both depend on the exact same impossible-sounding ingredient, some form of matter or energy that has a negative density. Let's start with wormholes. Physicist Kip Thorne did the math and figured out pretty quickly that any shortcut through space-time would be insanely unstable. Gravity would just slam the throat of the wormhole shut almost instantly. The only way to prop it open, to basically use a cosmic doorstop, is to line it with some kind of exotic matter that has negative energy. This stuff would have to be so weird that it actually violates a fundamental rule of physics called the weak energy condition, which pretty much just says energy can't be negative. To hold a wormhole open, you literally have to break one of the universe's rules. Now, the Alcubierre warp drive has a similar issue, but the scale is just mind-boggling. The original model from 1994, it needed a bubble of negative energy so huge you'd need the mass energy of the entire universe to create it. Yeah, a bit of a problem. But over the years, other physicists have tweaked the model. They've found different shapes for the bubble that slash the energy needs. First, down to the mass of a planet, then, in some newer models, all the way down to the mass of the spacecraft itself. So the physics says it's not forbidding, but the engineering challenge of creating that much stable negative energy is still, astronomical. So at this point, you gotta be asking a really important question. If this stuff is powerful enough to bend space-time and hold open tunnels to other galaxies, what's to stop it from just, breaking everything? And that's a serious question. If we could somehow create a big, stable chunk of negative energy, we could theoretically do some crazy stuff. We could cancel out the positive mass energy of a star, making it vanish. We could maybe even destabilize the vacuum of space itself. It really sounds like we're playing with cosmic fire here. So why hasn't everything just collapsed? Well, because the universe has safety protocols. Physics has these very strict rules called quantum inequalities, and they basically act like a cosmic governor on an engine. They say, sure, you can have negative energy, but only in tiny little bits and only for incredibly short amounts of time. The more negative energy you want to create, the less time the universe lets you have it. These limits are the very thing that keeps reality from just unraveling. So where does all this leave us? We've gone from a weird theory to a real measurable force, all the way to sci-fi dreams and the fundamental rules of the cosmos. Let's just kind of wrap this up and think about what it all means for the future. This is where we're at right now. We are no longer asking if negative energy is real. We've seen its effects with the Casimir force. We've got the equations that describe how it behaves. But that huge leap from seeing these tiny, fleeting effects in a lab to actually generating and controlling stable fields of it, well, that's still way beyond our reach. The key word, though, is yet. And in the end, that's what studying negative energy really is. It's like a little whisper from the quantum vacuum, a reminder that the basic rules of reality are so much weirder and more flexible and more amazing than we ever thought. It shows us that the line between science and science fiction, sometimes it's just a matter of time. And that leaves us with one final incredible thought. We've managed to crack the atom. We've mapped the human genome. If we, humanity, ever figure out how to harness the power of nothing, what other cosmic secrets are we going to find? And where in the universe will they take us?